So the answer here is just the average of those two, and that's 12.5%. Actually, what you already did, you already used the formula that I would like to introduce. So the return of the portfolio can be written as the portfolio weight times the return of the assets in the portfolio here. So that would be W1 times the first return plus W2 times the second return. So let's quickly fill out the remaining numbers here. So, and that's plus 2.5%. And we have plus 12.5%. Now again, once you have these three returns, you can apply all the formulas from the last chapter, right? You can treat this as a single security and use those formulas. The question is, can we maybe figure out the three solutions here in a different fashion, so not from these numbers, but tying it back to the numbers of the portfolios. And for this, we have to dive a little bit into probability theory, because our portfolio is basically now, we go back here, it's a combination of two random variables. The first random variable is this, and the second random variable is this. Right? So what is the expected value of the sum of two random variables? What's the variance of a sum of two random variables? And what's the covariance? So I'm going to show you all the relevant formulas from probability theory. They're always at the bottom. I'm not going to derive them together with you. So for that, again, I mentioned this I think last week. If you have some troubles with probability theory, we can maybe organize kind of a review part from some econometrics textbook or so that I can hopefully share on Moodle. I would have to check with the library what I can put online. But usually it's okay if I upload not more than 10% of the book. And usually it's allowed. If we have the book on the library, I can do that. Right, so if that's something that you find useful, then let me know. Okay, so the formula that we're applying now is this one here. That's the expected value of the sum of two random variables. R1 and R2 are random, and the two portfolio weights are just constants. Right? W1, W2 are constants. Right? The first thing is that we can take out constants of the expected value operator. And the nice thing is that this is additive, so you can rewrite this as the portfolio weight times the expected value of the first random variable plus the portfolio weight times the expected value of the second random variable. So the expected values are linear functions basically in their components, and you can nicely split this up. It's not true for all the risk measures, but for expected values, this works. Again, these here are random variables. So in statistics textbooks, you would find these usually as denoted as x and y, and this would be a and b, but formulas really don't change in their meaning. So that means that the formula that we have at the top here for the return can actually be applied also on the expected return. Right? So let me write this down. So the portfolio return is W1 times the expected return of the first asset plus W2 times the expected return of the second asset. So that's 50% times 9% plus 50% times 6%. And that gives us 7.5%. That's the answer. See, once you know what the expected returns of my components are, it's pretty simple to apply the portfolio weights and compute the return of your portfolio, the expected return. So this usually is much quicker than kind of doing it the way how we did it last week. Similarly, it works similarly quick for the betas. So it turns out that the betas are also linear functions in that sense. So let's write down the formula for our portfolio. So you can calculate the beta of the portfolio as W1 times the first beta plus W2 times the second beta. So again, if the portfolio weights are just 50%, that's easy. So the first beta here was +2. The second was minus 2.36. And the result is minus 0.18. Now if you remember how much time we spent last week on computing those covariances, right? That was a pretty long term, pretty long computations. But if you know those individual betas, it's pretty quick to compute the portfolio beta, right? You don't have to worry about the covariance formula anymore. So this is probably the one that is most useful or the quickest among all these formulas here. Now why is this the case? Again, we borrow a result from probability theory. So the covariance is also a linear function. So if you write down the covariance of the sum of two random variables with a third random variable, then you can split this up in the first covariance plus the second covariance, and then take out the constants as well. Right? So this is going to be equal to W1 times the first covariance plus W2 times the second covariance. And if you then divide by the market variance, which is the same in all betas, right, you'll go to the beta representation. So the reasons why we have this is because expected values and covariances are linear functions. It means you can nicely split them up. Unfortunately, the variance is not a linear function, the standard deviation, so this doesn't work for variance and covariance. So maybe let's go back to our numbers sort of table here. Maybe just quickly write down the results. So this was plus 7.5%. This was minus 0.18. Now, suppose we could apply the same formula for the volatility. What result would we get? Well, the average of this would be roughly 20.5%, right? Do you think that result makes sense?
Not such a big. Yeah, no, because they're too close to each other, so we will have probably the same amounts.
Look at the returns on the left-hand side for a second. Rethink this a little bit. So we've computed the volatility, right? It was high because we have very large deviations here, right? So minus 25 to plus 30, the difference is 55% the difference. Right? Here we have plus 50 and minus 5, again, 55% difference. How about this one? No difference. 12.5 minus 2.5, it's just a 10% difference. So they're all much closer to their expected value. So should they have the same volatility as these two, or in a similar ballpark? This seems to be much less volatile. Right? So, well, we've discussed the reasoning behind this already last week, right? So this one here is negative, this one is positive, right? These are positive, this one's negative, right? So the stocks are negatively related. Right, so that seems to be here a big factor because it leads to, first of all, a time series or a return series where all the returns are positive suddenly. Right? Don't make any loss, and they're all much closer to each other. Right? So we can try out the formula here first that we did last week to have the results here in one place. So sigma squared of the portfolio should be 20% times 12. Well, actually, we can simplify this even more. Let me do a quick version here. It's 20% for the first scenario, because the returns in here and here are the same, so I can add up the probabilities. So 12.5% minus 7.5% squared plus 50% for this middle scenario times 2.5% minus 7.5% squared. Right. That's a quick one. Right. Now if you take the square root of this, you actually get to 5% as the result. So it's significantly less than before. So we'll have this in the slides later on, but this kind of finding that we have here is quite surprising. Look at the portfolio, right? It consists of two assets with high volatility, but the combination of those two assets is much less risky. Right? It's below the risk of every individual component. Right? That's surprising that this can happen, and this is called diversification. Right? If you can reduce the risk in a portfolio, that's what we call diversification effect. There's several kind of ways of how you could see this, but this was very apparent, right? The portfolio here has much less risk than each individual component. And the reason for this is that those two things are negatively related. Right? When this one does a loss, we can compensate it with a profit here. We make a loss here, the profits compensate that here. Right? So if you can find these pairs of stocks which are exactly negatively related, then you can reduce your risk quite significantly. A nice example might be like you have a store that sells ice cream in the summer, but will probably not sell any in the winter or when it's rainy. But maybe when it's rainy outside, you have a company that sells umbrellas, right? They will do well when it's bad weather. Right? So those two businesses might be negatively related, no matter how the weather is. If it's raining, the umbrella company makes money. If it's sunny, the ice cream company makes money. And that would be a simple example to look at. Now, what we want to do though is, well, you see in this example, the old formulas from last week are pretty quick, but I want to tie back the number of 5% to these two numbers.